The first unit, that is electrostatics. The second unit, magnetostatics. That is what we are actually doing. And in the last three classes, we discussed about two important laws of magnetostatics. One is Biot-Savart law. Another one is Ampere's law. And we have studied extensively about that. And you also attended a quiz on that. So now we are moving to next topic, that is magnetic flux density. So the magnetic flux density will be very similar to that of the electric flux density, and the very similar description will be there. So we already have noted that this flux density is nothing but this epsilon electric field, where epsilon is the material property and the electric field what is passing that, and this describe the number of flux lines. So in a particular point charge, how this flux is excited out of that, or in a particular body shape, and in perpendicular to that it will be coming. So this also is equal to the, if you, it is also equal to the charge density of the particular structure. Here, if it is a volumetric structure, then we can say it is a volumetric one. So if you integrate this as well as this, then you will get the total flux, total electric flux, and which will be equal to total charge. So this is what we call that as a Gauss law. So here also we have similar description for the magnetic flux. I always tell you that wherever this charge is coming in the electric field, in that place you have to use the current. And similarly, wherever the dot product is coming in the electrostatics, you have to use the cross product. So very similar observations will be there. You can easily understand that. Also, we are going to see the force due to the magnetic field. So if a particular point charge is there, we know how this electric field induce the force upon that from another source charge. Similarly, how this magnetic fields apply the force on the charge, or in a current element, or in a surface. So how this is happening. Okay, so these are the topics there for CAT. So I think now we are here. So the magnetic flux density and the force due to magnetic field. So that is what we are going to discuss. So in the next class, I will cover up this remaining three topics, which are very important topics. So in case of magnetostatics, we have started with Biot-Savart law. So the Biot-Savart law tells very important thing that whenever there is a current flow, and that definitely will induce the magnetic field at a particular point P, and that can be calculated by this important expression. Here, this is the current which is flowing in the, and this is the line joining between the current element and the point P. And this magnitude can be used in the denominator as a R cube. So this is what, so this also indicate that how this magnetic field is flowing. So whenever there is a current is flowing, and we can apply the simple right hand rule, it says that the magnetic field will be just around that in the clockwise, in the anti-clockwise direction. So whenever the current is flowing in the opposite direction, then the field will be exactly opposite. So, and this is because of that, whenever there is a structure which are not infinite, most probably people tend to use the cylindrical coordinate system in order to describe the behavior of the magnetic field, which is just around that. And in case of Ampere's law, the Ampere's law tells a very similar description, but in the opposite way. So it is telling in the differential manner. This is telling in the integral manner. That's all. So whenever you are integrating a source, current source, using the closed surface, and if you can get all the magnetic field components, then you can calculate the total current. So it is, it can be also derived using another format, that if you know the surface of the closed structure, let's say this is the current carrying conductor, and you have a circle just around that, that is, we call that as the Amperian path. This Amperian path tells about the this tells about this dl, and therefore you can use this expression in order to collect all the magnetic field which is going around this line. On the other hand, if you know the surface, if you know the surface and which is perpendicular to this ds, and this vector also you know, and the magnetic field also know, then you can do the cross product with this. So this cross product will give us the small dh will come, which is perpendicular to this surface. And if you take a dot product of that, then you can again calculate the current density. So this is nothing but the current density itself. That is why when you integrate over the surface, you got the current. So that is what we call the Maxwell's equation. So this is the Ampere circuital law. So using these two expressions, you can calculate from a current source how the magnetic field, from a magnetic field how the current source, all the information you can find out that. If the structure is a little bit tricky, some a very complicated shape, and you know the current surface current density, and in order to collect all these things, sometimes it will be difficult. So what people used to do, they will divide this into multiple small portions. Therefore the vector differential calculus supposed to be used, and in that regard we have a smart method called uh, magnetic scalar potential, magnetic vector potentials. But these are very, very useful for time dependent structures. That is why I'm going to teach this in the whenever we have the time dependent, maybe just after the magnetostatics, we will start that. So these are the things we have studied. And next we are now going to magnetic flux. So this magnetic flux is very similar with respect to the electric field. So in that electric flux density, we have defined this D is nothing but epsilon E, where epsilon is nothing but epsilon or epsilon naught. If it is a vacuum, we can simply consider this as a epsilon naught. And similarly, in case of magnetic flux lines or magnetic flux density can be defined as this magnetic number of magnetic flux lines per unit charge, sorry, unit area. And this is a completely material dependent one. So that is why this magnetic permeability is also coming into the picture. It is very similar to that of this epsilon. So this epsilon tells that how far this magnetic field allowed in a given material or given region, and that is described. So if this, it is with respect to the vacuum. So if you take, let's say, SiO2, so this epsilon r equal to 3.9, which means 3.9 times higher electric field will be induced due to the due to that particular material. Okay, so it is also because of the electric field what is taking place there. So very similar expression we have here, and here the material property will come. So therefore, this permeability, whenever you have this mu r equal to 1, that is always referred as non-magnetic material. And whenever mu r is greater than 1, they are often referred as magnetic material. So magnetic material, we already have seen that they will be having the outermost orbit of the atom will be having two spins. Okay, out of this two spin, one will be not available. Therefore, only one spin will be there, and this spin will exert the magnetic field. And similarly, multiple atoms will create magnetic field in a particular direction that altogether will get that. And this description is defined with this mu, and which is nothing but mu r into mu naught. And here it is described for a vacuum case. So this mu naught. Okay, the mu naught again can be defined here. So that is the permeability of the free space. Now, this magnetic field lines, if you can integrate, then you will get the flux, total flux you can calculate, which can be calculated over a given surface. So this also a vector and this also a vector. Therefore, if you integrate this, you will get the total magnetic field. And that if you use a finite surface, if you use the finite surface, then you can capture only few lines, and those lines also will be completely closed, because this line anyway is going to close and once again is going to come back here. So there will be a going out and coming in magnetic field will be there. So this is what we have to keep, one of the important difference between the electric and magnetic flux. So if you take a point charge, it is going to exert the electric field, and that is going to describe the D. And if you draw a closed path, then you can capture all the field lines. But the interesting property is they won't come back, because this going outward direction, or sometimes it will come inward direction to the negative charge or something like that. The field will be going out, and in some place it will come back and it will go once again. So this is the tricky problem in the magnetic flux density. And this magnetic flux density is very much analogous to this total electric flux density. And the only important difference is the electric flux density always going in the outward direction or inward direction. Any one particular direction alone will be there. Therefore, the so-called the divergence, or the inward or outward divergence, is become meaningful. And this give a very important understanding that there will be a independent point charge is possible for the electric field case. In other words, the electric charge is quite possible as an isolated one. That is why it is either exerting or it is accepting the field lines within that. So it act like a source or sink in any of the particular way. So you can easily confine with the finite closed surface. You can do that. Okay. So that is why it is giving some meaningful value, and that is what we call total charge. But very similar description when we do for the magnetic flux, and if you try to draw a finite closed path, and what will happen, this flux lines always will go and will come back. It is become a closed path. So a closed path in it itself claims that. So there will be a let's say there is a closed path I have taking, and here the magnetic field I am taking, and on the other hand there will be an incoming magnetic field also. So this is actually going outward direction, this is coming inward direction. Therefore, the total magnetic field that is going to be zero only. So that is why in a finite closed path, if you try to calculate the magnetic field from a particular source, then obviously you will get zero. And it also tells that in this any particular point or from the source, you will find both the source field and the sink field also will be there. So that is why we have north and south pole together all the time, and you can't separate that. So uh, always uh, magnetic charges are dipole in nature, and the electric charges are monopole in nature. So that is why you can't get a magnetic monopole, is almost impossible. There are huge amount of research are going on how to get the magnetic monopoles, and whether such a behavior is meaningful or not. That kind of discussions are going on, but it is almost impossible to get the magnetic monopole. And this give a very important question on this phrase of the so-called the magnetic charges. So we have a electric charge due to the meaningful electric flux lines, and when you integrate that, you can get some value. But here, this magnetic field, obviously, when you integrate over the finite surface, it becomes zero. If it becomes zero, does it mean that there is no source or there is no sink? And if we say that there is a source and sink, then what is the meaning of that? And another thing, here we have a separate dedicated term called electric charge. Similarly, do we have any magnetic charge? There are many debates are going on that always there could be a magnetic charge, but this magnetic charge always will be having two uh, charges together, and one will be exerting, one will be accepting. So both will be available in a uh, uh, integrated manner. So by the way, the electric field, whichever is generated, will be synced by this itself. So this we call one of the very important concepts in the field of magnetostatics, that is called chirality. So a electron, whenever it is going around the atom, so it rotates. At the same time, in another place, it is also taking it. So this kind of property it is very difficult to define mathematically. So this is why actually Paul Dirac has come up with one of the very complicated phenomena in quantum mechanics that is called chirality. So the chirality tells that if you see this orbit in the flat line, in one particular point, the electron spin will be like this. The another spin time, the electron spin could be like this. So this will follow a kind of a loop like this. So this is the, you can also search for the term chirality of electron. It's one of the very puzzling term. And when we break this, people are saying that you can get this asymmetry of magnetic charges. But but the question is whether such a structure is stable or not like that. Maybe in the very extremely low temperatures, it could be possible. At that time, we can't distinguish what is electron, what is photon, anything else, which we call that as a, what do you call, a Bose-Einstein condensate. So this kind of interesting phenomena is happening because of this definition of the magnetic flux itself. And because of that, you can't divide into this north and south pole. Always when you divide, this you already studied in the school. And I'm not sure whether you have understood in this level. This give a direct simple expression that if you have a finite surface and try to calculate the magnetic flux over that given surface, you always will get 0. Okay, so this dot product clearly indicate that with respect to that particular surface, then the magnetic flux supposed to be perpendicular. That is why we are getting 0. On the other hand, there are another assumption that there is always source and sink magnetic flux sources and sinks together. So this is also the meaningful one. And this tells that within the given space, always the magnetic field will be conservative. Okay. It is the same thing you have also seen in uh, the for the electric flux, which tells that a single charge will follow that. So that is the conservation theorem there, and here it is. This is the second Gauss law of magnetostatics, where the first Gauss law of magnetostatics is Biot-Savart law. And when you take the divergence theorem, so divergence theorem says that this volume integration, so sorry, the surface integration can be converted to volume integration. So for that, you have to take the dot product of this B, and that also going to be 0. And in that case, this del dot B becomes 0. And this is the fourth Maxwell's equation. So this tells that the non-existence of the magnetic monopole. So that is the secret behind that. All these Maxwell's 4 important equations we already derived with a simple, very simple one-page on one slide itself. We have explained how this behavior is. So here there are 2 things about the electric and 2 things about the magnetic. And if you see that this and this tells about the non-zero quantity, and there are 2 zero quantities. So whenever there is a dot product with magnetic field, you will get 0. Whenever you take the cross product with the del, you will get the 0, which in other words, it tells the conservative, or there is a point charge either as a source uh, or a sink can be possible, but it is not possible in terms of magnetic field. On the other hand, if you the electric charge is it is also telling that the electric charge is nothing but the electric flux, or vice versa. And similarly here, the magnetic flux or the magnetic field is nothing but the current, or current is the magnetic field. Like that, some of the physical understanding is coming out of this Maxwell's equations. So when the very first time Maxwell realized this, he was actually, he got fever and he could not do anything, and he resisted to take food and other things. With such a similar behavior we can see in many of the great scientists, even Paul Dirac and in their even Boltzmann, such a scientist, when they understood this physical nature of the space, they realized some weirdness. I don't know whether you got such behavior as a symptom of genius. You can tell about that. Anybody got fear or something else while you clearly understood the physical nature of the system? Anybody has such experience? Okay. Okay, you might
Yeah,
not
like
be,
when I read about time traveling or like the black hole, I got little feared. So
of course, of course. Yeah, maybe if you extensively study this electric and magnetic field, means electrostatics and magnetostatics, I hope definitely we can clearly understand that. You can also try to do this exercise, which is available in HATE. It's a very simple derivation how to calculate the magnetic flux, which are for a infinite coaxial cable, where this current is going in one particular direction, current is coming in another direction. But three different or four different points, how this magnetic flux, which we already calculated using Ampere's law. This also you can try out with this similar Maxwell's fourth equation. And another very interesting and important topic, which are very, very useful in the practical world, is force on the force due to the magnetic field on a particular charge. We already studied the very first equation is this, that is Coulomb's law. The Coulomb's law clearly tells that from a source charge, another test charge, always force will be exerted because of the electric field, which is exerted from the source charge, which is defined in this way. So this electric field and force will be following the same line, same direction. And the very similar expression you can also do for the case of magnetic field. But the only difference is the charge actually supposed to move, because then only the current will takes place, and because of that current only electric magnetic field is accepted. Similarly, in order to act or the force should be acted on a charge, the charge supposed to be moving. Okay, in other words, if a particular point charge is stationary and there is no change with respect to time or space, then there won't be any so-called velocity. And if there is no velocity, it first of all, it cannot create any magnetic field. At the same time, it may not be affected by the magnetic field. So in both the way you can observe that very similar to that of this the uniqueness theorem what we have studied. The very similar principle also can be applied here. Uh, so this is the way the force on a particular point charge, which has the q, and with the velocity of the charge. So this is the velocity of the charge. It is moving by itself, or through external force also it is moving. Let's say you are moving the point charge by some mechanical force or something. And therefore, the magnetic field is perpendicular to that and will apply the magnet. So if both the point charge and the magnetic field, if they are in both directions, for example, this is the direction of the magnetic field. You have a magnet here, and this magnet is actually creating magnetic field, and in this particular direction the magnetic field is available, and the point charge is moving in this direction. So because of the magnetic field, there won't be any change in the direction or in the velocity. Nothing will happen because both are in the same direction. Due to this cross product, there is no change. So whenever this is actually having some direction with respect to this magnetic field, and there is a angle, then it start to deflect. And so we can see that because of the force, there will be a change in velocity. Therefore, the acceleration will change. So that is what the effect of magnetic field on a moving charge. So it is clearly says that when the U is 0, then obviously force supposed to be 0. So for a stationary charge, there is no force due to the magnetic field. And these two very first time is actually connected by Lorentz, and he also proved various concepts, and that is what we call Lorentz force equation. So this, by adding both, you will get the expression for Lorentz force equation. This is actually one of the most important and uh, uh, influential equation, not even for Lorentz himself, for many important scientists, including Einstein. You just imagine that this Lorentz force equation was explained by Weber to Einstein. So because of that, uh, so you just imagine that how this historical moment could have been. So whenever there is a magnetic field acting on a particular moving charge in a particular, then you can easily explain that in the force acting on that, and it will be starting to change the velocity as well, and therefore it start to move in the other direction. So we assume that this is the direction of mm, the moving charge, then it start to bend over that, and likely it start to move in a circular manner. So that is what we can easily infer out of this expression. So if there is a point charge and both electric and magnetic fields are available, electric and magnetic field both are available, then due to this electric field, this point charge slightly start to move. Immediately after this movement, there will be a increase in U. This U will, because of the U, there will be a force acting on the uh, the point charge due to this magnetic field. And by the way, this again, this will start to change the velocity. So because of that, some interesting phenomena is going to happen. So that is summarized here. So this is the Lorentz force equation, and we have this electric field and magnetic field. Both are available, both are perpendicular to each other, and assume that this particular point charge is uh, is actually trying to move uh, in this in any particular direction. Let's say it is moving in this direction or in this direction, whatever it is. So these are the two possible direction it's supposed to move, because the magnetic field, if it is moving in this direction, there is no sense about that with respect to the magnetic field. So now we are assuming two things. One is the electric field is zero and B is alone available. Okay. In that case, this charge, whenever it tend to move, and it will immediately affected by this magnetic field and tend to follow the path. So let's say this is actually moving in this particular direction. Then according to this, so this is the moving direction and where the U vector is available and this magnetic field is available in this direction. So perpendicular to that, it start to move. So the perpendicular direction is this. And just in a few moments, this will start to go in this direction, in this direction, in this direction, like that. It will start to move perpendicular as much as possible, and therefore it will start to flow in a circular manner. So that is when the absence of the magnetic field, sorry, electric field. And in the next case, if you assume only this electric field alone and magnetic field is zero, then what could have happened? So the point charge is moving in this direction with the velocity of v, and what will happen? This electric field will tend to make this in its own direction. This is the very simple thing, because the force will be in this particular direction. So slowly this charge will tend to move in the perpendicular direction and will make it in the vertical direction in this way. So this is what happening when the electric field alone is available. And here both are available. So the electric field will be in this direction, and magnetic, due to this magnetic field, the the perpendicular to both u vector as well as b vector along this particular direction, this the field, sorry, the uh, velocity will try to change. So because of that, the charge whichever is starting in the particular direction, it will try to go in a spring like, or we can say that it is helical shape it will follow, and that is the basic behavior. And this is the very similar behavior we can see that in most of the chambers wherever the electron or not only electron, ions, let's say hydrogen or some phosphorus or something, whenever, so we can easily control its path. And by the way, the velocity of in the starting u naught and velocity after some time will be very high. So this is one way of accelerating the charges. And we can also do it for atom, which where one or two electrons will be taken out of that, they will be immediately charged. And one can easily see that as much as you take the number of charges out, this both it's, let's say you have this Fe, it has many outermost electrons, and when you try to remove 3 electrons, then it will become plus Q, and if it's become plus 3Q, then the force also will increase. On the other hand, you will get more magnetic field will be self-induced by it, which in other words, its permeability will become high. And by the way, this become highly accelerated. And this is actually, but this doing this job is very difficult, atomic physics aspect. So that is why the people, they can't use metal for this kind of atomic energy purpose, but some gases they can easily do this all ionization, all this is. But it is still most probably uh, like some of the ceramics or some of the uh, gases alone being used for such a atomic studies. And so this directly we can connect this force with the ma, where m is the mass of the charged body, and this du by dt is nothing but the acceleration. So both are once again is changing. And here comes the very important thing, that this side there is no time, and where only space is available, and this side you have this with respect to time. So both are available, and this is one of the very important space-time continuum equation, which often refers continuity equation. So here we have both the continuity in terms of electric and magnetic fluxes available. So this is very, very powerful equation, can solve many of the things, including the motor, and then many things like generator, and in many ways actually is used. Let's take a simple example. We will understand that how this phenomena works and how to calculate that using by hand, actually how analytically we can calculate the force, and force due to the magnetic field, force due to the electric field, and how this velocity and acceleration changes over the time. All these things we can easily understand. So here there is a charged body is there, and it is 2 kg, and it has 1 coulomb, and it is actually traveling in a particular direction. And at the origin, it is estimated that its velocity is 3 meter per second along the y direction. So the velocity is along the y direction, and in that particular region, there is a uniform magnetic field where B is equal to 10, and that is actually traveling along the z direction. And now our job is at time, at initial time as well as at time t equal to 4 seconds. What is the velocity and acceleration, and then the magnetic force acting on that. We're supposed to remember that most of the details are already given. For example, velocity at time t equal to 0 is given, and acceleration, of course, it will become 0 then. And the magnetic force acting on that, we can easily do that by simply taking the cross product of them. We will get the force angle. But at time t equal to 4 seconds, how, what about the velocity, acceleration, as well as the magnetic force acting on that we supposed to calculate. For this, we supposed to use this equation, and we have to solve for the time. Okay, in the previous cases, we would have calculated with respect to space, x, y, z, or with respect to cylindrical coordinate system. But here we are going to include time as well. So you will get 4 dimensions, and so this will give some intuition about in terms of space-time continuum as well. So we got the equation F is equal to ma, which further we are writing that m du by dt, which is nothing but q into u into b. So this is because we have only magnetic, and the electric field is equal to 0. So this problem will become a little tricky if you have electric field also. Now we are actually going to rewrite this one. So how we are going to rearrange? So this m, we are actually going to bring it to the denominator, and we got this expression. So what we can say that using this expression, we can calculate the time dependent uh, u, that is nothing but the acceleration we can find with respect to the charge and the mass, the velocity and the magnetic field. So this four thing, how it is influencing with respect to time, we can calculate. So the simple thing is the acceleration can be calculated by this qm, which is constant, and ub, we are going to take the cross product. So first we will calculate this cross product. So here the cross product we can easily calculate. So first let us put this u vector into b vector. So when you do the cross product, what we generally do is nothing but we will write the unit vectors, and first we will fill the u vector, then the magnetic field. So when we fill it, ux, uy, uz, and in case of magnetic field, it is available only in the y direction. So therefore, in the other directions they are zero. Only in the y direction we are substituting the magnitude. And yeah, here this q is the q is 1 coulomb, and this m is 2 kg. So it become 1 by 2 kg. That's all. So now when you multiply, since so with respect to ax, what you will get? You will get plus 10, and with respect to y, you will get once again this and this and this and this. So you will get a y term will be available. A z term will become 0 because both the terms here are 0. So you got this equation. So here you got 1 by 2. So you will get 1 by 2 10 ux ax vector minus 10 ux ay vector. So that is what you will get. And this 10, now it is replacing this 10 with a 5. So that is what we got here. So this is nothing but the acceleration. And this acceleration can be further divided in terms of uh, axis by itself, because we have to multiply with this d by dt. So we can take all these terms separate because they are completely independent each other. So that is why we have taken this. So this first term, second term, we got this two. And the third term is going to be 0. In other words, the velocity is constant along that particular direction. So in fact, in that particular direction, only the magnetic field is available. Because of that, there won't be any change in the direction, so that anybody can easily understand out of that. Okay, so for this we already can see that the c naught. Now we have to calculate the c naught value. But before that, we'll try to solve this expression. Now, if you carefully notice this, d ux by dt, which is nothing but phi uy, and duy by dt is nothing but minus ux. So here ux uy, it is this way it is connected. So now, can you say that how to solve this equation 1 and 2 simultaneously? Anybody has idea about that? So let me do here dux by dt, which is nothing but say m times uy, and duy by dt is nothing but n into ux. So this is the equation 1 and this is the equation 2. Now we have to solve this equation simultaneously. It is a differential equation. So how to do that? How easily we can do that? Can anybody tell it? See, if you have this, let's say, okay, so 4x equal to 3y and 3x equal to 2y something, 2y equal to 3x means you will substitute here and you will compare it. Similarly, how to substitute this one? How to substitute this dux by dt in this equation 1? Can anybody tell? It is very simple. I have given the clue. Okay. So normally we do here some kind of substitution, is it? We will multiply or add something. Here in the differential equation, we have to differentiate, that's all. So when you differentiate this equation 1 with respect to time, we will get square and d by dt will come. So this can be substituted here and you will get everything in terms of ux and you can easily solve that. So that is what it is done over here. So the equation 1, first actually we are actually differentiating with respect to time. So you will get du dx d square ux dt is equal to 5 into du, which is nothing but we are substituting the equation number 2. So by this you got the simple expression and you are actually bringing this into the left hand side, you got this expression. So you have to solve it. So for simple differential equation, the solution is nothing but exponential equations. So this exponential equations has two solutions, two perpendicular solutions. One is cos and sine. So that is the easiest answer. So you can easily put a constant and then cos root of this magnitude, which is nothing but m square. Now you can write mt. And similarly sine mt, here it is c2. So that is the solution for ux. Now, how to calculate this uy? So here we have the answer that if you differentiate with respect to time, you will get this y and this we can bring it to this denominator. So you can write that uy is nothing but 1 by 5 into dux by dt. So that is what actually it is done over here. And by the way, you will get this. So both are having the common constants C1 and C2. Now we have to calculate this C1 and C2. So how to do that? We got now the velocities in terms of time. So time t equal to 0 when you substitute, then everything can be calculated. At least the initial or the which we call boundary condition. So that first initial condition can be calculated. So we are going to substitute t equal to 0. So when you substitute t equal to 0, so you will get cos, it will become 1. So C naught will exist and C2 will disappear. So C2 will be disappearing and C1 alone will come. At that particular direction, we have to calculate what is this ux. If you notice this from the given question that velocity is available only along the y direction. Therefore, this ux supposed to be 0 only along at least at the time t equal to 0. You should remember this. Not at different time, only at time t equal to 0, it is equal to 0. Therefore, when you substitute this equal to 0, you will get the value of C1, which is nothing but 0. And what about along the y direction? At time t equal to 0, this uy is equal to 3. So uy equal to 3. Therefore, at that particular time, time t equal to 0, C1 yeah, once again C1 will exist for at time t equal to 0, 3 equal to along, okay, here. So this is uy. So when you substitute t equal to 0, you will get this term becomes 0 and this term will exist. So you will get C2. C2 is nothing but 3. It is very easy to do that. Next, we are having this uy. We already know about that uy is uz is going to be 0. So uz equal to the initial condition. And again, very similar to that of that along the z direction, there is no component. Obviously, this is also going to be 0. So you can easily calculate the u in terms of time and which also satisfy the initial condition. That is a very important thing. So when you take t equal to 0, you will see that this term becomes 0. This term will exist, which is nothing but 3ay vector. So that is correct. So now we got the time in terms of the velocity in terms of time, we got that. So now we can see how this will at time t equal to 4 seconds, we can easily calculate. So that is what we are going to do. So at time t equal to 4 seconds, when you substitute the sine term, initially it was 0 at time t equal to 0, but hereafter it won't be 0, which in other words, the velocity will be available also in the x-axis. So what is the meaning of that? So let us assume that this is y-axis, this is z-axis, and this is the x-axis. So this is where the velocity. Okay. So the particle is actually moving in a particular direction with the velocity of uy vector, and the magnetic field is available. So obviously the force will be available in this particular direction, and which we can expect only in the x direction. So at the initial time, this is the velocity, but later time, this velocity will take both x and y. So it will be available here, available here. So after huge amount of time, it will become perpendicular. So which in other words, there is no y vector, only x vector will be available. That might be the time where this particular term become 0. So it might be that it cannot be, because sine 0 only you will get, and next you will get at 2 pi, where 2 pi is nothing but 2 into 3.141, which is approximately 6 point something. So when this value is about 1 point some seconds, then it will become 0. Sorry, this will become 2 pi, which at that particular time it might come as 0. Therefore, only this vector will come. So next time this will happen, and it will start to flow in the circular manner. So that is what actually described in this particular u vector. And similarly, we can also calculate this differential version of that, and then we can substitute this 4. Then you can calculate this force. Acceleration you can calculate, and once the acceleration is calculated, since you know the mass, you can calculate the force acting on that. So this is the force acting on that, and now we can also calculate the same thing in the other way. Since the velocity is available and b is available, when you take the cross product, also you can do that. So there are two methods you can do to calculate the force acting on a particular moving charge in a particular direction due to the magnetic field in the perpendicular direction. So this is a very simple workout, but it is quite meaningful with respect to the magnetostatic theory. So I believe you have understood this. Okay. So this is what the magnetic force on a charged particle. The same theorem or same exercise can be done for current elements, as well as we can also do for surface. We can also do for volumetric currents. All these things actually we can do it. And interestingly, if this velocity this velocity what we have here, it is available in a particular direction. Let's say in a free space the charge is moving, but if it is available in a conductor, okay, and how this force will be happening, so that we can study using this simple phenomena where we will use Biot-Savart law to do it, and then we can also do it for a loop. And if you do it for a loop, let's say rectangle loop, then you will get this interesting behavior. If you notice this, at the initial time it is 0, but due to the electric field induced upon that, it start to move fast in the magnetic field. So this is the very important thing. As this magnetic field is constant, then this coil tend to move in a great velocity. So one has to control that saturation velocity. So that is the interesting part in the motor. For that, so this we will see in the next class. And then after finishing this, the same exercise can be converted as how this two loops are coupling each other, and there comes mutual coupling between mutual magnetic coupling, where the inductance will come into the picture. So both inductance and force acting on a current loops, and then magnetic energy, these three things we will see in the next class. And by the way, this magnetostatics will be completed. So you will get all these things for the CAT exam. So you start to practice. If you have any questions, I'm ready to answer for that. The class is over. You can leave if you have any. What?
Sir,
Hmm?